that we learned last class period because it's been since Wednesday since we had a lesson, right? So it's been a while. So on Wednesday, we talked about two theorems in section 5.1. The first theorem was the perpendicular bisector theorem. And it said that if you have a perpendicular bisector and you have a point on that perpendicular bisector, what is now true? Very good. So make sure you guys are with me reviewing this right now, trying to get it stuck in your head so you can remember it. The perpendicular bisector theorem said that means AB is now congruent to AC. Okay, and then the converse went the other direction. If I don't know it's a perpendicular bisector, but I do know these distances are equal, then that means that this line must be a perpendicular bisector. Okay, the second theorem we talked about was the angle bisector theorem, and it said, maybe, if you have an angle that has been bisected, split into two congruent parts, and you have a point on that angle bisector, what do we now know? Okay, AD is now congruent to AC. And again, I'll just remind you, it's super important that those are drawn perpendicularly so that you know that those are the same distance. If I walk to the wall perpendicular or I walk to the wall diagonally, those are two completely different lengths. So it's super important that those have little right angle boxes. Okay, the converse of that then said you don't know this is an angle bisector, but if those distances are congruent, then that must be an angle bisector. Okay, then we took them to triangles in section 5.2, and we had, if I have a triangle and I draw in all the perpendicular bisectors, so I'm going to do this really quickly, it's not going to be very good, pretend that it is. This is going to be really bad because that's not really the perpendicular bisector. But, okay, what did we call that point if I drew in all the perpendicular bisectors? The circumcenter. Be careful, not incenter, circumcenter. If you're drawing in perpendicular bisectors, this was the circumcenter. And what did the circumcenter theorem say? Very good. So the distance from here to A, here to B, and here to C would all be the same distance. So from the circumcenter to the vertices, equidistant. All right, then the second and last thing we talked about with the triangles was if I draw in all the angle bisectors, so now those are going through the angles, splitting all of the angles into two congruent parts. And again, I'm doing a really messy job here, but pretend it's nice and neat. All right, what did we call that point? The incenter. Okay, so these are the angle bisectors. And the incenter theorem said what about the incenter? Anybody help her out? Very good. So the distance from the incenter to the sides is all equal or equidistant. And again, anytime we draw that distance, we're drawing it perpendicularly to those locations. So all three of those distances were the same. Okay, what was the name of the circle that went around the outside of the triangle? What kind of circle is that? Circumscribed circle. And what kind of circle is inside the triangle? Inscribed. Okay, all of those things need to be quick in your mind. You need to have those down because now today we're going to add on two more points of concurrencies in our triangle and talk about more line segments. So 5.3 is all about medians and altitudes. So first of all, we need to know what is a median, what is an altitude, and then we're going to draw those inside our triangle and look at two more points of concurrency that are created. Okay, so if you're looking at 5.3 with me, first of all, a median. Make sure that you understand the difference between a median and a perpendicular bisector. Okay, perpendicular bisectors do not have to go through the vertex. They do split the side into two congruent parts, but they have to form a right angle. A median is a segment whose endpoints are the vertex. So it must go from the vertex. Medians have to go from the vertex, but they also bisect the opposite side. They do not have to form a right angle. So it is going to go to the midpoint of the opposite side. So a median goes from the vertex to the midpoint. It's going to bisect, but it does not have to make a right angle. It does have to go from the vertex. Everybody clear about the difference between a median and a perpendicular bisector? So if I drew a perpendicular bisector on this picture, it would still go through point D, but it would have to make a right angle. So this blue line would be a perpendicular bisector. The red line is a median. They could be the same thing, depending on what kind of triangle you have. If I had an isosceles triangle and I drew the median and the perpendicular bisector, they would both end up being the same thing. This would be my perpendicular bisector, and this would also be my median. So it can be that they're the same thing, but they do not have to be the same. Does everybody see the difference? Okay. So just like with the two on the board over here, I'm going to erase these, and we're going to draw another picture. So if I were you on my notes, I would create a little triangle somewhere. And we're going to draw in all the medians of our triangle. Draw in all the medians. So a median, again, goes from where? Vertex to where? Okay, where on the opposite side? The midpoint. So we're going to go from the vertex, and we're just going to estimate right now, just to make this quick. We could use a ruler and measure, but we're just going to estimate where that midpoint looks to be. And then do that for every side. Go from the vertex to about where you think the midpoint should be. And when you're doing this, if we did it accurately, the three medians would be concurrent, just like last class period. So when you draw them, make sure that yours does go through the same point. You may have to fudge it a little bit since we're not using an actual ruler and measuring. But they should all intersect at the same common point. And if we did it precisely, they would. Okay, so median goes from vertex to midpoint, and they do intersect at a common point, so the medians are concurrent, just like the perpendicular bisectors and the angle bisectors. If it is a point of concurrency created by the medians, it has a special name, and its special name is centroid. Okay, the centroid is the point of concurrency of the medians. So this point where they meet is called the centroid. Centroid. Okay, this time in the notes, they do not create all three triangles and talk about where its location is. So I want you on your notes somewhere to go ahead and do this with me. This triangle I drew was acute. So go ahead and create a right triangle and an obtuse triangle, and let's investigate where does the centroid land. So I'm going to do a right triangle, and I'm going to do an obtuse triangle. But I don't think I put that in the notes anywhere on this one. So once again, we're going to draw on all the medians and see where it lands. Where's the centroid when it's acute? Inside. So it's always going to be inside. And you may want to make a note where you're putting this on your paper, just like we did last class period, that this is the kind of questions you'll see on your test for the always, sometimes, never questions. Okay, so the centroid is always inside an acute triangle. Okay, do it for the right triangle, draw on all your medians. So from the vertex, estimate where you think the midpoint is, draw in the median. I'm going to keep saying those words, so hopefully it'll stick in your mind. Median goes from vertex to midpoint. Median goes from the vertex to the midpoint. And make sure that they do intersect at a common point. So kind of fudge that till they do. If it's a right triangle, Where is the centroid going to land? Inside as well. So where do you think it's going to land if it's obtuse? Let's check it. So we're going to go from the vertex again to the midpoint. Estimate where you think that is. Draw in your median. Vertex, the midpoint of the opposite side. And then vertex, the midpoint of the opposite side. And where did it land? Inside. So the centroid is always inside the triangle. What point last class period, circumcenter or incenter, was always inside the triangle? Incenter. So this one was also always inside. Remind me, where was the circumcenter when it was a acute triangle? Inside. Where was it if it was a right triangle? Okay, on the hypotenuse, and it was specifically on the midpoint of the hypotenuse, but it was on the triangle. And where was it if it was obtuse? It was outside the triangle. Okay, keep that in mind for later today. So that's the things we've learned so far. And now the centroid is always inside, and it's made by the medians. Got to keep in mind what makes these things, okay? So that's also part of it. Okay, the centroid is one of the most special points of concurrency. It's got a lot of things special about it. So the first thing that's special about it is the centroid is also called the center of gravity. So you're going to have word problems, and on the word problem it may not say find the centroid. It may say find the center of gravity. And you have to know the center of gravity is the centroid. Okay? Kind of helps that they sound the same when we start talking about them. Center of gravity, centroid. Maybe that'll help you remember. The reason it's called the center of gravity is because it is the point where a triangular region will balance. So it may not even say find the center of gravity. It may say find the balancing point. And you need to know, okay, the balancing point is the centroid. All right? Because of that, because it's the point where it will balance, it's the center of gravity, there's going to be a shortcut of how we can find our centroid. And that's what Bree was mentioning early at the beginning of class, and we'll talk about that in a minute. Okay, so if you were to take a triangular shape and you wanted to balance that on one point, that point that you would need to find would be the centroid. Okay, it's directly in the middle of that triangle. Just like all of these, each one had a theorem about it that was true. The circumcenter was equidistant to the vertices. The incenter was equidistant to the sides. The centroid has a special theorem about it as well. So it's called the centroid theorem, and here's what it says. It is not equidistant to anything. Okay? That's those two from last class. The centroid is going to split each median. So here's my centroid. It's going to split each median into two pieces, right? So for example, on this one, I've got BP and ZP, two pieces. When it splits your median into two pieces, it's going to split them so that one of those pieces is 2/3 of the entire median, and the other piece is going to be 1/3 of the entire median. So the centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. To me, that's a little bit wordy. I like to write it this way, so maybe you want to add this in your notes. Vertex to centroid is equal to 2/3 of the median, or you could write it as centroid to the side of the triangle is equal to 1/3 of the median. So centroid to the vertex is 2/3, or centroid to the side is 1/3. Okay, so for example, Let's say that BZ is equal to 15. That whole length is 15. What is the distance from P to Z, the centroid to the side? 5. 1/3 of 15, which is 5. So what's the distance from B to P, vertex to centroid? 10. 2 of those thirds. What do you notice about the relationship between the 2/3 and the 1/3? If this is 5 and this is 10, what's always going to be true about the 2/3 compared to the 1/3? Exactly. This 2/3 part will always be 2 times the 1/3 because 2 times a third is 2/3. Does that make sense? Okay. And so the way they wrote it here was that AP was 2/3 of the whole thing, BP was 2/3 of the whole thing, CP was 2/3 of the whole thing. You could have also written it with the 1/3 parts. So I'm going to go back and write that below here if you want to add it to your notes. So if I'm dealing with this AY piece, then PY would equal 1/3 of AY because it's the 1/3 part. If I'm looking at the blue BZ one, then the shorter piece is PZ. So I could say PZ is 1/3 of BZ. That's a 1/3. It looks like 1/8 there. That's 1/3. And then if I'm looking at the red CX line, then PX would be the short part. So PX would be equal to 1/3 of CX. So you can write it either way in terms of the 2/3 or the 1/3 part. Big idea though is a centroid splits a median into 2/3 and 1/3. Vertex to centroid is the bigger piece, the 2/3 part. I'm going to add that up here. So this would be the 2/3 part and this would be the 1/3 part. Everybody clear on centroid theorem? All right, so first thing we're going to do is look at some problems where we're trying to find these things. And I think you have 2 examples that are identical, but they ask you for 2 different things, correct? Okay, so on the first one it says in triangle LMN, RL is 21. So this whole thing here is 21. SQ is 4. So this little piece right here is 4, whereas the red piece, the entire thing, is 21. And they want us to find LS. So we're looking for LS, which is this piece right here. So is that the 2/3 part or the 1/3 part? 2/3. So you can either just think about it in terms of fractions and numbers if you can do that really well, or you can write equations. And so I'm going to show you both ways. So if this is the 2/3 part, in my mind I think, okay, if 21 is the whole thing, and I divide that by what? 3, then 1/3 would be how much? 7. And if this is 2 of those thirds, then what should it be? 14. So if you can do that in your head, then you can just say LS is 14. Or if you need an equation, you can say LS is equal to 2/3 of the whole thing, RL. And then you can plug in what they give you. RL is 21, and so you can do 2/3 of 21. 3 goes into 21 7 times. 7 times 2 is 14. So if you need an equation, write an equation. If you can just think about it mathematically, that's okay as well. Any questions on the first one? Okay, what does the second one ask you to find? I'm not going to switch the picture, but what does the second one ask you? NQ, okay? So NQ is equal to. So if we go to the picture, what is NQ? Is it the 2/3, the 1/3, or the whole thing? The whole thing. So again, if you can think mathematically, what is the 4 representing? The 2/3 or the 1/3? 1/3. So if one of the thirds is 4, what is 2 of the thirds? 8. So that means this missing part in S is 8. So what does that make this whole thing in Q? 12. So then you can just say NQ is equal to 12. But if that doesn't work for you and you're still kind of confused with fractions, then write yourself a formula. So you're looking for NQ. NQ is the whole thing, but you know the 1/3 part. So you know that SQ is equal to 1/3 of NQ. They give you SQ, So work backwards to find NQ. If I'm trying to solve for NQ, I would just multiply both sides by 3. So multiply by 3, multiply by 3, the 1/3 and the 3 cancel, and we get NQ is equal to 12. So if you're not quite sure with the numbers, then ask yourself, what's the relationship between the two objects I have, the one they gave me and the one I'm looking for, and write an equation. Any questions? Okay. So then the next thing we have here is the example like last class period, but if you remember last Wednesday, we didn't go over this example where it was graphing in class, correct? I sent you a little 9-minute video. Did you guys watch that video or at least look in the book? Okay, so you were supposed to figure out how to find the circumcenter if it was given as a graph. Guaranteed question you'll see on your test. So here's another question, guaranteed. If you want to make yourself a note, you will see this on your test. Super important. Okay. This one says a sculptor is shaping a triangular piece of iron that will balance, there's the key word, that will balance on the point of a cone. At what coordinates will this triangular region balance? So you get to the test and you have to ask yourself, what is the point called where it balances? And today we learned that's called what? Centroid. And then you have to remember, okay, centroid is made by drawing in what kinds of line segments? Medians. Then you have to remember what's a median. A median goes from where to where? Okay. Vertex to the midpoint. Okay, so the long way to work this problem, I'm going to show you both ways so that way you can choose what works for you. I'm going to show you the long way first and then I'll show you the shortcut, okay? The long way is just like for the circumcenter. You would draw in for the circumcenter at least 2 perpendicular bisectors. You need at least 2 so you can see where they cross, right? Same idea here, except we're dealing with medians. So you would draw in at least 2 medians to see where they cross, and then you would just write the coordinates for the centroid where they intersect. So that means I want to go from the vertex to the opposite side's midpoint. Notice that none of these sides are vertical or horizontal, so it's not going to be a quick little shortcut. We're going to have to use our midpoint formula. All right, I'm going to go from 6, 6 over to this side here and draw in my first median. So let's find the midpoint of this blue side. Remember, to find the midpoint, you just average your x's and average your y's. So what am I going to add first? 8 plus 10 and divide by 2. And then what am I going to add next? 7 plus 2 and divide by 2. Okay, so what does that simplify to? 9, comma, we have 7 plus 2, careful, 4.5 or 4.5, either way you want to write it. So then we have a midpoint at 9, 4.5. So we're going to go to 9 and up to 4.5. Plot that point. Use a ruler when you're doing this so you can be precise. Otherwise, you won't be confident where they cross. Okay, so if you want to grab a ruler, you can real quick, or just make sure when you get to the homework or the test that you are being real precise, okay? So not like my little freehand crooked line that I just drew. Okay, that's one median. Again, how many medians do we have to find the centroid? At least 2. Okay, you don't have to have all 3 because as soon as 2 cross, we know the third one's going to have to go through that same intersection point. So at least 2. So does it matter to you which side I do next for the midpoint? Okay, then I'm going to do this side and go from this point here. Okay, vertex to midpoint. So let's find the midpoint of this side. So what am I going to add? 6 plus 8 and divide by 2. And then what will I add? 6 plus 2 and divide by 2. Okay, let's simplify there. What's 6 plus 8 divided by 2? 7. And 6 plus 2 divided by 2? 4. So then again, you're going to graph that point, 7, 4. And then draw the line that goes from the vertex to the midpoint. And again, use a ruler, make sure it's very precise. Okay, where does it cross? 8.5. And again, if you're not sure, get a ruler, make sure your lines are straight, but it should be crossing right there at 8.5. So your answer would be that the balancing point is at 8.5. Make sure you list the coordinates because that's your answer. It's not the picture of the graph. It's not a dot on the graph. It's the coordinates for that point. Any questions on how we got that? Okay, here's the shortcut, and it works every time, but only for centroids, okay? Because it's the center of the triangle, the center of gravity, it is directly in the middle. You can find it just like you would find the midpoint by averaging. You can average, this time though, what we're averaging are the vertice points. How many vertice points are there in a triangle? 3. So instead of adding and dividing by 2, we're going to add and divide by 3. So the shortcut for finding the centroid, and you can do this every time, it's up to you. You can graph it if you want to, and you can work it the long way, or you can do this shortcut. And the shortcut for centroids only is to average the x's. So this time we'll have 3 x's, x1 plus x2 plus x3, and divide by 3. And then you can do the same thing to the y's. Average the y's. y1 plus y2 plus y3 divided by 3. And that's using those vertice points. And that will give you the direct center of your triangle. Okay, so let's check it and see if it really does work and we get 8.5. We'll just do it verbally. So what is 8 plus 6? 14 plus 10? 24. And what is 24 divided by 3? 8. So that's exactly what we got. Let's try the y's. What's 2 plus 6? 8 plus 7? 15 divided by 3? 5. And that's what we got. Much faster, much easier. You don't have to graph. You don't have to find midpoints and draw lines. Super easy. Questions on the shortcut? Okay, but is everybody with me? It only works for centroid. Does not work for circumcenter. So if it's the circumcenter, you have to do like we did in the video that you watched, where you have to draw in at least 2 perpendicular bisectors and find out where they cross. Okay? All right. All right, last line today in 5.3 is the altitude. So we said this is going to be about medians and altitudes. So medians, vertex to midpoint. Now we're going to define altitude. When you think of an altitude, just in general in life, when you hear the word altitude, what do you think of? Say it again. Height, right? Height. If I think about the altitude of an airplane, I'm thinking about how high up in the air is it. So altitude is your height of your triangle. The altitude of a triangle is a perpendicular segment that goes from a vertex. So just like the median, it has to go from the vertex. It goes from the vertex to the line that contains the opposite side. And they word it like that because there's some instances where it can't go to the opposite side without extending that side out. And we'll look at that. Every triangle will have 3 altitudes, and so once again, when you draw those in, they're going to be concurrent, and you're going to have another point of concurrency. So on your paper right now, again, it's not in your notes, draw 3 triangles. We'll do altitudes here. Draw an acute triangle. Draw a right triangle. And then draw an obtuse triangle. We're going to draw in all the altitudes and look for that point of concurrency and figure out where is our point of concurrency. Okay? So altitudes by definition have to go from the vertex perpendicular to the opposite side. They do not have to bisect like a perpendicular bisector. They just have to make a right angle. So for example, on my acute triangle here, if I want to draw in the altitude, I start at the vertex and I draw a line straight down that makes a right angle. It could be a perpendicular bisector. It could go through the midpoint. It does not have to. Okay, and most of the time it won't. Go to the other vertex. Draw a line that looks like when you draw it over to the opposite side is making a right angle. And then do your last side. Opposite vertex to the opposite side, and it looks like it's making a right angle. And again, if we were really doing this accurately, we would use a protractor, we would measure the 90-degree angle and then draw our line, but we're just estimating today to make this quick. So now we have this point where they all intersect in the middle. And that again is a point of concurrency, just like all the other ones, but we're going to be specific since it's made by altitudes. So if it is made by altitudes, we call it the orthocenter. Orthocenter. So that's our last point of concurrency. It's called the orthocenter. Again, for your vocab test, the orthocenter is the point of concurrency of the altitudes. The point of concurrency of the altitudes. Where is the orthocenter if the triangle is acute? Inside. It's always going to be inside if it's acute. Okay, let's go to the right triangle. We're going to draw in all the altitudes. I'm going to start with the right angle's vertex first and go across to the opposite side and make sure it looks like it's making a right angle. To me, that's the easy one. But sometimes we get confused when we go to the other vertices. So for example, up here, where am I going to draw the altitude from that vertex to make sure it makes the right angle with the opposite side? Straight down. So it's going to turn out to be one of the sides of your triangle, which makes sense because when we talked about finding area of a right triangle back in chapter 1, we did base times height divided by 2, and we used the bottom of the triangle, and our height was the side of our triangle, right? Okay, and altitude is just your height. So if I go over here to this vertex, where am I going to draw the line so that it makes a right angle with the opposite side? Okay, so again, horizontal right down that leg. So where do all three of those lines intersect? Right. On the right angle on the vertex. So it is on the triangle, right? And it is on the right angle's vertex. But the biggest thing I want to make sure you know is that it is on the triangle. Okay, last one is the obtuse triangle, and this is the one where they say the line containing the opposite side. So we'll look at what happens here. I'm going to start with the obtuse vertex. So start here with this obtuse vertex, it's the easy one. Go across to the opposite side and make a right angle. Okay, the problem occurs then when we go to one of the two acute angles. So I'm going to start up here on the top. If I want to draw a line that is an altitude that has to be perpendicular to this side, can I do that by going to the actual side? No. So that's why in the vocabulary it said the line that contains the opposite side. So you have to extend out this side. And then you draw the line perpendicular to that line. So it's going to go straight down perpendicular to that. Does that make sense? And I didn't extend my line out very straight there, so pretend that's straight. Okay, same idea when we go to this next one. The last acute angle's vertex. I can't draw a line over to these opposite sides and make a right angle. So what I have to do is extend out that side. So I'm going to extend this out. And then I'm going to draw a line from that vertex perpendicular to this line. Do those three altitudes intersect right now? No, but keep in mind that these are line segments. If I extended out those altitudes, so if I kept drawing this straight down, I kept drawing this one, I kept drawing this one, this was not very good, and kept drawing this one, would they intersect? Yes. And again, with me estimating these, it doesn't turn out perfectly, but if we used a protractor and we actually drew in the right angle and made sure, you would be able to see that they do. And that's what this picture in your notes is showing you. The black triangle is the obtuse triangle. The red lines are the altitudes that they have drawn from each vertex over to the opposite sides. So notice how they had to extend out a couple of those sides. And they did intersect right here at a common point. Okay, so that common point, one more time, what's the name of that common point if it's made by altitudes? Orthocenter. All right, and where is the orthocenter if it's obtuse? Outside the triangle. So one more time in your notes, these will be the kinds of questions that you will see on the test, always, sometimes, never. Now, the orthocenter, it does have stuff special about it, but at our level of mathematics and geometry, we haven't learned enough information for me to show you the real reason behind the orthocenter. I can tell you that there's a famous mathematician named Leonhard Euler who came up with Euler's line, which relates these points of concurrency to each other and develops an equation that goes with that. But you need some higher level mathematical understanding in order to tie it all together. So there's not in geometry a theorem that goes with the orthocenter like we had for all of the other three. There's not going to be anything special about it that we're going to learn right now. So at this point, we just need to know there is an orthocenter that's created by the altitudes. It does exist even in an obtuse triangle. It's just outside the triangle and you have to extend out your altitudes. But there's not going to be a special theorem that says it's equidistant to something or that it splits it into 2/3 and 1/3. So there's not another relationship you have to memorize. Okay? Any questions about the orthocenter? All right, the orthocenter is made by altitudes, and again, the altitude is just the height of the triangle. So the last example you should see in your notes is another graphing problem where you've got to find the orthocenter. So I want to make sure when we get to the test, you kind of have this all wrapped around in your mind as well. The first lesson, I did not go over the example. I sent home a video. You watched it on how to find the circumcenter by graphing. You graphed the triangle, you drew in the perpendicular bisectors, and you found out where they crossed, right? Today we talked about the centroid, and the centroid we said we could do by either graphing and drawing in two medians, or we could do the shortcut and find the average of the vertices, right? So the third one that you could see on your test, we can't do incenter because it's made by angle bisectors, and you can't do that on a graph without using a protractor, and it wouldn't be a coordinate plane activity. So you won't see incenter on your test as far as a graphing problem. So the last one you're going to see is orthocenter. Grab a sheet of graph paper and go ahead and graph this triangle. I should have said this when you jumped up out of your chair and grabbed graph paper, but you will definitely need a ruler for this one or a straight edge of some sort. So if you don't have a ruler or a protractor, so sorry. But this will keep you awake, jumping up. Grab a ruler or a protractor. And since we're missing Marissa today, I am going to go ahead and do this on the whiteboard. But I will tell you that my graph's not drawn very well. Yours is going to be better because it is accurate. Don't freehand your graphs on homework. Always use graph paper. And so mine may not turn out as perfectly as yours is going to on your paper. And if you're watching this video, I will also send out some pictures of the board that I drew everything on for you to look back at as you're watching the video as well. Okay, so we want to find the orthocenter. So again, to me, the hardest part of this, each individual topic is not tough, but you put it all together on the test and you see the word orthocenter and you have to think, okay, what kind of lines make an orthocenter? So today, what kind of lines make an orthocenter? Altitudes, which isn't so bad since we just talked about it. But 2 weeks from now when you're taking a test, or 3 weeks from now when you're taking a test, because we have a week of Thanksgiving break in the middle, trying to go back and remember that it's the orthocenter is the hard part, right? So we need to remember that orthocenter is made by altitudes, and altitudes go from where? From the vertex. Careful, not bisector, but perpendicular. So it does not split it into two congruent parts, but it does make a right angle. So it has to be perpendicular. How many altitudes do we need to draw to find the orthocenter? 2. You could draw 3, but you don't really need that third one. As soon as 2 lines have intersected, you know the third one's going to go right through that same point. So you just need 2, even though there are 3 altitudes. Okay, so if you're lucky, you'll have one side or maybe both sides that are either vertical or horizontal. But it's highly likely that you won't have both of them being vertical and horizontal. So in this case, here's one that's vertical, which will be the easy side to draw it to, but then the other 2 are going to be a little bit harder. So to draw our altitude, we're going to go from Z. If I want to go perpendicular to this opposite side and it's vertical, what kind of line do I need to draw? Horizontal. So I'm going to go straight across here horizontally to this opposite side and make a right angle. It's when they're diagonal that it becomes just a little bit harder. Again, not hard. You just have to be careful and think about what you're doing when you're graphing this. So do you guys want to go from X to the opposite side or from Y to the opposite side? I don't care. Okay, Bree says Y. So we're going to go from Y over to this opposite side. Okay, so if I'm trying to go from Y over to the opposite side and I want to make sure that it's perpendicular, what would I need to do graphically to make sure that my line is perpendicular? Very good. The first thing I need to do is find the slope of XZ, the line I'm trying to draw it to. And I don't want my line to have the same slope. What kind of slope will my line need to have? Opposite reciprocal, because remember, perpendicular lines have opposite reciprocal slopes. So first we'll find the slope from X to Z, and then we'll find the perpendicular slope with the opposite reciprocal slope. So what is the slope from X to Z? Okay, I'm going to go up 3, so that's a positive 3. And then Anna said we go right 4. Do you guys agree? So that's a positive 3/4. So what is the perpendicular slope? Negative 4/3. Where will you start from and use this negative 4/3? At Y, okay, the opposite vertex, the one you're trying to draw it from. So you find the slope of the line you're trying to draw to, and then flip it and change the sign, and then go to the point that you're trying to draw it from to start. So that means we're going to go down 4, right 3, from Y. Do it on your paper. Is it on your line YZ, or is it off of it a little bit? It's off a little bit, and I need you to see that. This one is so close, but it is not really on the line. So when you draw this blue line, I'm going to draw up here, to make this perpendicular, it is not crossing at point Z. Even though it is super close and almost looks like it's on that line, it is not on that line. And if you want to be confident, find the slope from Y to Z, and you'll see that the slope from Y to Z is not negative 4/3, and so you'll know it is not that side. If you'll use a ruler, you can be really precise. So this is the hardest one of them all today, because it crosses right here That is not a whole number, right? Does everybody see where it's crossing on your paper? It's not a whole number. It's not at 7, 1, although it's really close to z, which is at 7, 1. It's not exactly 7, 1. So we're going to have to solve for that point of intersection. So this is going to connect our Algebra 1 to our geometry. All right, so in Algebra 1, you graphed lines, and you found out where they crossed. And sometimes that was nice and pretty whole numbers. And then you learned in Algebra 1 that that doesn't always work. They don't always give you nice, pretty whole numbers. So then you talked about another way to solve for the solution, which was by substitution or elimination method. Writing a system of equations, taking those two equations, and solving it that way algebraically. Does that make sense, what you guys did in Algebra 1? So what we're going to have to do is write the equation of this green line and write the equation of this blue line and then solve that system of equations to find out where they cross. That way we can get an actual correct fraction for our point. Okay, so let's start with the green line, and this is going to take us back to Chapter 3 when we wrote equations of lines, which also was review from Algebra 1. What is a horizontal line always going to look like when you write its equation? Careful. Y equals. Be careful. It is the y that never changes. X is constantly changing, but y never changes, right? So it's going to be y equals what? Y equals 1. So our equation for the first one is just y equals 1. That's easy. Just horizontal. Okay, now we're going to go to the blue line and write an equation. We could do slope-intercept form, but we don't know where it crosses the y-axis, and so that's probably a little harder to do. The easier one would be the point-slope form, which we reviewed last class period. Y minus y1 equals m times x minus x1. And the reason that one's going to be easier is because we know a point for sure on that blue line, and we know the slope of the blue line, so we can just plug those in. What was the slope of our blue line? Negative 4/3, so we can substitute that in. And what is a point guaranteed on that blue line? Y, the point we started at, right? So we know the coordinates for y are 3, 6, so we can just substitute those in for x1, y1. Is this making sense? Okay, so I'm going to have y what? Y minus, use your coordinates for y. What is the value for y1? 6, so y minus 6 equals negative 4/3, and then what are we going to have in parentheses? X minus 3. So now we have this system of equations, this equation and this green equation, and we want to solve that system of equations so that we can find the point where they intersected. Okay, again, guaranteed question you're going to see on your test. So if I were you, make myself a note, go back, study this example. So if I have y equals 1 and then I have this equation, what would be the easiest way to solve this system? Exactly. Using substitution method, we could just substitute 1 in for y. Since we know y is definitely 1, we already have what y is. We can substitute 1 in for y and then solve for x. Okay, so let's do that. So I'm going to substitute that 1 in. I'm going to work over here where I have a little bit more room. So I have 1 minus 6 equals negative 4/3 times x minus 3. Just plugging the 1 in for the y. What is 1 minus 6? Negative 5 equals negative 4/3 times x minus 3. What do you want to do to solve? Distribute the negative 4/3. So if we distribute that, we're going to have negative 5 equals negative 4/3 x. What happens when I do negative 4/3 times negative 3? Positive, and what is it? Okay, what is 12/3? Positive 4. The 3 and the 3 just cancel out, so instead of multiplying that, you could just cancel them and see that it becomes positive 4. But it is okay if you do 12/3, just make sure you reduce that. Okay, from there, what do we want to do? Okay, subtract the 4. So now we have negative 9 equals negative 4/3 x. What do we do from there? Exactly. We're going to divide both sides by -4/3. And then this takes us back to our arithmetic proficiency review. How do I divide with fractions? Okay. First, I need to make 9 a fraction. So this is -9/1. And then what do I do? Multiply by the reciprocal. So what's the reciprocal of -4/3? -3/4. Don't confuse that with the perpendicular slope is the opposite reciprocal. We're just multiplying by only the reciprocal, which is just the flipping. We don't change the sign. Okay, and then we just multiply straight across. What is -9 times -3? +27. And what is 1 times 4? +4. And what is 27/4? Okay, so it is 6 3/4 or 6.75, however you want to write it. So what are the coordinates of our orthocenter where this point is on our graph? What is this point, the orthocenter, going to be? 6 3/4, 1. So close to Z. Z is at 7, 1. So close, but not exactly. So sometimes you're going to have these nice, easy problems where they cross nice and pretty at a whole number right on your graph, and sometimes they're going to be fractions. If it's fractions, then you just need to write the equations of your two lines and find out where they intersect by solving your system of equations. And what I love about this problem is it makes us use our algebra skills, because when you go to Algebra 2 next year, this is the kind of stuff you're going to be doing, not necessarily with geometry triangles, but you're going to be solving systems of equations again. It's just when you get to Algebra 2, your systems are going to have 3 equations with 3 variables instead of 2 equations with 2 variables. So the more we can practice those things this year, the easier it'll be for you next year. Okay? Questions on 5.3? Okay, let me give you something that may help you organize all this in your mind. So when I first started teaching this, I had never learned this in high school. I don't remember it anyway. Didn't use it in college, points of concurrency, but I had to have all of this straight in my mind and be able to teach it and present it and make sure I wasn't doing a bad job and it wasn't confusing students. So I came up with a little acronym that helped me memorize what are my 4 points of concurrency, what kind of lines make those points of concurrency, and where are they, inside, outside, or on the triangle. So I'm going to show you what I came up with. If it helps you, write it down, study it, use it. It'll help you on the vocab test too, because on the vocab test you're going to have to know what's the point of concurrency of the perpendicular bisectors, the point of concurrency of the angle bisectors, the point of concurrency of the medians, and the point of concurrency of the altitudes. And this little acronym will help you organize that, okay? So it's called psychopoma, which you can always think, do you have a psychopa or a psychoma? Did your mom or dad ever get a little psycho at times? I probably do. At any football game, I'm probably a little psycho. But it's not spelled psycho like you really spell psycho. So first of all, let me make sure I'm teaching you correct grammar. So this is how you spell psycho. It's not the psycho that I'm using. We're going to spell our psycho C-I-C-O, and then PAMA, P-A-M-A, okay? Or you could think about it as sicko. But psychopoma. Do you have a psychopa or a psychoma? Psychopoma. Okay, so here is what these letters stand for and how it's going to help you. So and another thing that helps me is when I learn, if I can remember it the way I learned it, so in order. And again, this was for me, so if it doesn't help you, don't use it. But if it does, and you're like me, then this will be helpful. So we learned circumcenter first. So the first C is circumcenter. And the first letter over here, P, stands for the types of lines that make the circumcenter. What kind of lines make the circumcenter? Perpendicular bisectors. So P stands for perpendicular bisector. So the first letters go together. Perpendicular bisectors make the circumcenter. Okay? The second point of concurrency we learned was the incenter. And it goes with the second letter over here. So what type of lines made the incenter? Angle bisectors. Notice there's two A's. So what helped me keep them straight is I keep my bisectors together. P has to be perpendicular bisector, so the first A is going to stay bisector, so it's the angle bisector. Keep your bisectors together. So in-center is made by angle bisectors. Okay, the third point we learned, which was the first one today, C stands for centroid. So notice that there's two C's. So that kind of messed me up when I was trying to come up with a way to remember it. But when I was in high school and I was in English, my teachers taught us a rule in grammar that said I before E except after C, such in words such like neighbor and way. Did you guys learn anything like that? I before E except after C? Okay, Cooper says yes, he did. Anybody else? Okay, if that doesn't help you, you're going to have to come up with some way to remember which C is which. But what I remembered was I before E, so it's the CI, then the CE, because I thought back to my grammar rules of I before E, except in words like neighbor and way, because you spell neighbor N-E-I and way W-E-I, but I before E. Okay, that doesn't help you come up with your own way. But the second C, the third word, is centroid, and today we learned what makes centroids. Medians, and so the M is medians. And then the last point of concurrency we learned that starts with O is orthocenter. And it'll be easy to figure out the A that goes with it because remember we're keeping our bisectors together. So the first A has to be angle bisectors. So the last A stands for altitudes. So that's going to help you on the vocab test for sure because it keeps straight which point of concurrency goes with which kind of line. It's also going to help you on the test if it says find the orthocenter. You can remember, oh, that's made by altitudes. Here's the other thing that it's going to help you with. The always, sometimes, never questions. So remember that there were 2 points of concurrency that were always inside the triangle. Which 2 points of concurrency were always inside? In-center and centroid, right? If you look back over at centroid today, inside, inside, inside. Notice where they are in the word, psycho. They are both inside the word. So the in-center and the centroid are always inside the triangle, just like they are inside the word. Does that make sense? The other 2, the circumcenter and the orthocenter, look back at the relationships between those. The circumcenter was inside if it was acute, outside if it was obtuse, and on the right triangle if it was a right triangle, right? Think back to last class period, or excuse me, think back to today with the orthocenter. It was always inside if it was acute, outside if it was obtuse, and on if it was a right triangle. So do you notice that they have the same characteristics? So that's how I remembered it. These 2 are the same in that acute is inside, a right triangle is going to be on. It's just they're on different places, but the question will not be as specific as on the hypotenuse or on the vertex of the right angle. It'll just say on, inside, or outside. And then if it's obtuse, it's outside. And so that is the same for the ones that are on the outside of the word psycho. Okay, I hope that helps you a little bit, and if it doesn't, please don't worry about memorizing that because it's just a tool to try to help keep it all straight in your mind. Okay? Any questions on the 4 points of concurrency or any of the things that we just talked about in 5.3? All right, 5.4 is going to be kind of a little different, and it is just 1 page, and it's 1 theorem, and that's all there is to it. So it'll go pretty quick. So 5.4 is just the mid-segment theorem, okay? The mid-segment theorem for the triangle mid-segment theorem. So the first thing we have to do is talk about what is a mid-segment. So the definition for mid-segment of a triangle is just simply a segment that connects or joins the midpoints of 2 of the sides of the triangle. So it takes a midpoint to a midpoint. Be careful you don't confuse that with the median, which goes from the vertex to the midpoint. A mid-segment goes from midpoint to midpoint of two sides of your triangle. So for example, XY would be a mid-segment because it's connecting midpoint on this side to midpoint on this side. Does that make sense? Okay, because a triangle has three sides, it's going to have three separate midpoints, one on every side, right? Which means if you connect midpoint to midpoint, how many mid-segments can you get in a triangle? 3. So there are 3 mid-segments, and that's what they're showing you here. XY, YZ, and ZX are all mid-segments. And they connect and create this little triangle in the middle, which is called the mid-segment triangle, because it's made by the mid-segments. Is everybody okay with that? What do you think the relationship between the area of the mid-segment triangle and the area of the big triangle is going to be? Naya? Very good. So this triangle in the middle is going to be congruent to all of these triangles. So if that's the case, what would the area of this triangle be compared to the area of the great big one? 1/4. Does that make sense? Okay. All right, so this triangle is going to be a fourth of the big triangle. It's going to make 4 congruent triangles inside, and it's called the mid-segment triangle. All right, the next example is going to discover the formula. But because we're short on time, we are going to do this, but I'm not going to go through and discover the formula or the theorem. I'm just going to go straight to the theorem first, and then we'll come back and look at this longer problem that you'll see on your homework. And we'll do the easy ones first. So here is the mid-segment theorem. The mid-segment theorem is basically just 2 things. The mid-segment theorem says that if you take the mid-segment of a triangle, that mid-segment will, number 1, be parallel to the opposite side of the triangle. So first of all, every mid-segment is going to be parallel to the side it's not connecting. So if you look at the picture here, DE is the mid-segment, so it's parallel to which side? AC. And the second thing that's going to be true for every mid-segment is that its length will be half the length of the side that it's parallel to. So in other words, if AC is 10, what is DE? 5. So the triangle mid-segment theorem just says 2 things. A mid-segment will be parallel to the third side, and it will be half the length of the third side. Does that make sense? All right, and every mid-segment will have that characteristic. So you'll have problems like this one, where it says find each measure, and they're asking you to find the length from B to D. So again, to me, the hardest part of this is when I get to the test, all of this stuff's put together. And I have to look at this picture and try to decide what in the world is drawn on this picture. Do I have perpendicular bisectors, angle bisectors, medians, altitudes, mid-segments? What's in the picture? So go with the markings. Notice how these are congruent. So what does that make point B? A midpoint. These 2 are congruent. So what does that make point D? A midpoint. These 2 are congruent. So it makes point F a midpoint. And then ask yourself, what does that make line segment BF? Mid-segment, because it's going midpoint to midpoint, not vertex to midpoint. Does that make sense? So BF is a mid-segment. What else is a mid-segment? BD is a mid-segment. What else? And FD. And so you have the 3 mid-segments that are making that mid-segment triangle. Okay, so the hardest part is just looking at your markings and trying to decide what do I know from my markings. Then the math becomes really easy. They want you to find BD. We learned just now that BD is parallel to which side? AE. And we also learned that BD then is half as much as AE. So what is BD? Careful. 8.5. So half of 17 is 8.5. Everybody with me? Okay, so I really don't think, and you guys can correct me if I'm wrong, but have you felt like the math of this lesson or this whole chapter has been hard as far as like calculations? It's not hard math. Like sometimes you get into some algebra stuff that's tough, where you have to solve systems or factor and solve with quadratic formula, and some of that can get harder. But the math here is pretty easy. It's all the theorems and putting them all together, which is kind of geometry in general, right? It's all the theorems and putting it all together. Okay, here's another one, and this is going to take us back to chapter 3 when we had parallel lines cut by a transversal. So now remember, if a midsegment's parallel to a third side, then you're going to have all these transversals cutting those midsegments. And so you're going to have things like alternate interior angles that are congruent, corresponding angles that are congruent. So look at the picture here. They want us to find angle CBD, this angle right here. Okay, they give us that this angle right here is 26. So what I want to make sure you see is the lines that are parallel and the transversal that's making those angles. So first of all, we have this midsegment FD, and it's parallel to which side? AC. So do you see that those two lines are parallel? Therefore, what transversal are we looking at? Not BF, BD, because that's the transversal that's going to create the angle we're looking for and the one that they gave us. Now do you see what kind of angles those are? What kind are they? Alternate interior, made by the two red lines that are parallel and the transversal that's red that's parallel. And so what do we know about alternate interior angles? They're the same. So yes, this angle is how much? 26 degrees. Now, some other things that could pop up in the homework. Don't forget, if you have two angles that form a straight line, what kind of angles are those called? Linear pair. And what do linear pairs always add to equal? 180. So maybe they give you an angle and they ask you to find the one that's supplementary to it. So don't forget about things like that. Also, what do all three angles in a triangle have to add to be? 180. Careful, circle's 360. There you go. Triangle is 180. Okay, so things like that could pop up when you're working the problem. But big idea that you need to remember is parallel lines cut by a transversal. Your alternate interior are congruent. And also, I'll point out here real quick, so are your corresponding. So once we know this angle's 26, what other angle with those green lines would be 26? Not DBF. Look at the green lines being parallel. This angle, which is made by this transversal. BAF is correct. This angle right here. Do you guys see what kind of angles are those? Corresponding, okay? So watch for things like that too. And it may be hard to see at first. You may have to draw your lines with different colors like I've been doing and kind of get it to really pop out. Okay, any questions on those? All right, last longest example today is the first one that I skipped. And it is just going to ask you to basically show the midsegment theorem. So it's going to be a lot of work, not hard, just long. Okay? And it's all about showing, so you don't want to cut steps and not label and just write down numbers because that's not the goal here. So it gives you some information about the vertices of a triangle, and then it gives you some more information about midpoints, and it says show. And so this means you have to label your work and you have to show detailed, correct work. They want you to show two things. They want you to show these two lines are parallel. So first of all, on a graph, how can we show that lines are parallel? Same slope. So we need to show that they have the same slope. And then the second thing they want you to prove is that MN is half of XY. What is that going to require us to use on our graph? Distance. Remember, two capital letters side by side, nothing above them means distance. So we're going to have to use our distance formula. All right, so first thing you're going to need to do is graph that triangle. So really quickly, if you will, on your graph paper, graph it. And again, I freehanded mine, so it's not going to be as perfect as yours, but they should look somewhat similar if I did it correctly. Okay, so you have your triangle. I would probably label it X, Y, Z just to make sure that you have everything graphed and labeled correctly. And then it tells us M and N are the midpoints of XZ and YZ. So the next thing we're going to need to do is graph M and N and find what are their coordinates. And we're going to assume that that is respectively in that order. So M is the midpoint of XZ and N is the midpoint of YZ. Okay, so let's find the midpoint of XZ. So next thing we're going to do is midpoint of XZ. Show your work because it's all about showing, right? This whole problem. So midpoint from X to Z, you can use your coordinates for X and Z up here, -1, 8, and 3, -4. I'm just going to use my midpoint formula. So I'm going to add -1 and +3. So -1 plus 3 and divide by 2. Are we good? And then 8 and -4. So 8 minus 4 divided by 2. And that's going to simplify to what? +1 and +2. So then we're going to graph that. That's going to be the letter M. M is at 1, 2. So go to 1, 2, and hopefully it lands on your line. Mine's close. Yours should be perfect. So there's my M. And now we're going to do the same thing to find N. So second thing we're going to do is find the midpoint of YZ. So using our formula and using the coordinates for Y and Z. So I'm going to add 9 plus 3, divide by 2, and then 2 plus a -4, or 2 minus 4, and divide by 2. And then simplify. What's 9 plus 3? Divided by 2. So we get 6, and then 2 minus 4, divided by 2, -1. And that's going to be the coordinates for point N. So on your graph, plot that point, 6, -1. And then we can connect those 2 points to draw in line segment MN. And what kind of line segment, one more time, is MN according to the lesson today? Mid-segment. And so we're just trying to prove that it's parallel to the third side and half the length of the third side, which is the theorem. We're trying to show that theorem is true. So let's start with slope. So the third thing we're going to do is prove that MN is parallel to XY, so we need to find the slope of MN. And since it's on the graph, you can just count your rise over your run. So what is the rise and the run from M to N? -3/5. Everybody agree? So the slope is -3/5 because we went down 3, right 5. Then we'll find the slope of the line that it's supposed to be parallel to, XY. So go ahead and do that. What's your rise and your run from X to Y? Anna says down 6, right 10. Somebody agree with her? Okay, so we have -6 over 10, but that can reduce. What does that equal to? -3/5. And then you're going to tell me, what does that mean, that since they both had the same slope? That's what they told you to prove. So this proves, so state it on your paper, MN is parallel to XY. The work proves what we're trying to say. Okay, and then we have one last thing to do, and that is find the distance. I'm going to have to go through that pretty quickly so we can get done before the bell rings. So number 4, we're going to find the distance from M to N, and then we're going to find the distance from X to Y. Using our distance formula, which is the square root, we subtract the X's and square them and add the difference between the Y's squared. So I'm going to use my coordinates that we just found for M and N, which are 1, 2, and 6, -1. So that's going to give me 6 minus 1 squared, and then -1 minus 2 squared. I did X minus X, Y minus Y. I'm going to simplify that. That's going to give me 5 squared plus negative 3 squared. Simplifying that gives me 25 plus 9, which is the square root of 34. And I know I did that really quickly, but we should be okay with distance formula, right? Okay, I'm running out of room on the whiteboard. I'm going to try to come down here low for xy, xy, and I'm going to do the distance from x to y real quick. So x to y, I'm using the coordinates up high, negative 1, 8, 9, 2. So I'm going to have 9 minus a negative becomes plus 1 squared, plus, and then 2 minus 8 squared. Simplifying that, we get 10 squared plus negative 6 squared. Simplifying that, we get 100 plus 36, which is the square root of 136. We need to simplify that. Okay, I'm just going to go ahead and tell you that 4 goes into that so that I have the square root of 136. I'll show it up here where you can see it better. It's going to factor into 4 times 34. Okay, and if it factors into 4 times 34, then 4 factors into 2 times 2. 34 is 2 and 17. So I have a pair of what? 2's. So that's going to become 2 square roots of, and I multiply them back together, 34. And then you're going to show, last step, that this is, square root of 34 is half of xy. So you'll write down mn is equal to 1/2 xy, and then plug in your numbers and show it. Mn was the square root of 34. That equals 1/2 of 2 square roots of 34. And what happens when I take a half of 2? They cancel out. So I get square root of 34 equals the square root of 34. And I proved that that was true. Okay, that was really fast. So if you missed something, just fast forward on the video to the very end and you can rewatch that little part, okay? Sorry that was so quick at the end. Here's your assignment, and Thursday will be much less stressful and busy. By the way, we will go over the test on Thursday. I'm sure you're wanting to see that. I didn't want to take the time because the lesson was too long today, but we will go over it on Thursday. You will need graph paper for homework. There's one for you and Anna, one for each of you guys, one for each of you guys. Thanks for being so amazing, guys. Have a great day.